And this guy over here is... Okay, so we are recording now, and we will continue with the electronic structure, and we will discuss the electronic configuration of ions. I did cover it last time, but we'll do more. So electronic configuration of ions, and then that actually relates to ionic bonding. So there's a connection between these two. Then we will look at the trends in the periodic table. Okay, and you are going to discuss this in the lab. You're going to do the experiments in the lab. So there is a periodic variations, trends in the periodic table that relate to the size, which is the atomic radii, the ionization energy, which relates to formation of ions, and the electron affinity, which is the electronegativity. Okay, and hopefully there is time, then we can start with the covalent bonding, the electronegativity and the bond type and the polar and non-polar. At least I want to start with that. And then next time when you come, we will do the Lewis structures. Okay, so first of all, let's get back to the electronic configuration of ions. So the electronic configuration of ions. Now, ions are two types. One is the cation. The cations are positively charged, and this also, like I said, these two are connected, the formation of ions and this part on the ions and the ionic bonding. These two things are connected. So in a way, we are starting off with chapter 7 also. So anyways, the cations are those species which are positively charged, and the charge is positive because the electrons are given. Electrons are lost, or either lost, or you can also say they are given away. Okay, then the next is the metals are going to form cations. So all the metals will lose electrons. Next is the anion. Now anions are those species that have a negative charge, and how many negative charges or how many positive charges, that depends on how many electrons are lost or gained. So here in the case of anions, the electrons are gained, so they accept the electrons. The metals give away electrons, and the non-metals accept the electrons. So generally the non-metals will make anions. Okay, so this is one piece. Now first of all, let's look at the electronic configuration. And then I'm also going to include here ionic bonding. So let's look at configuration of ions, and we will also look at the ionic bonds. So this is from the next chapter. This is on from your chapter 7. Okay, chapter 7, ionic bonding. So I don't have to repeat it again and again. So ionic bonding is when the electrons are transferred. So the ionic bonds are formed by the transfer of electrons. Okay, transfer of electrons. So either lost or gained. So transfer of electrons, and the driving force behind it is the octet rule. Now octet rule is octet. Octet means 8. Okay, 8 electron rule. So 8 electron rule applies to the noble gas configuration as well. Noble gas configuration. Now, except helium, because helium doesn't follow the octet rule. So the noble gas, all the noble gases except helium. So let me write this down here. All noble gases, all noble gases except helium have 8 electrons in their last shell. Now, what is a last shell? Last shell is also called a valence shell. This is also called a valence shell. And valence shell is the one with the highest shell number. Highest shell number. Highest shell number. Okay, now let's look at the electronic configuration of sodium. Very simple ones. Let's look at sodium and chlorine. So when they combine, then they form sodium chloride, which is the ionic compound. ionic compound. So it has ionic bonds. Okay. Now, ionic compounds, like I said, made up of ionic compounds always are going to be made up of metal, and this metal will always have a positive charge. Okay. And this, when metal combines with another non-metal, then this non-metal will have a negative charge. Okay. And the metals can also combine with polyatomic ions. Okay. And these polyatomic ions also have negative charge. So PAI means polyatomic ions. So let's look at first the situation between sodium and chlorine. So sodium has 11 electrons, like the mass. So this here is the atomic number. So anytime you're looking at the electronic configuration, you look at the electronic configuration, you look at, so from now onward, I'm going to just write down for electronic configuration, I don't have to write this big letter, a big number, like this big word. So I'm going to just write down EC config, econf. Okay, so this is what it means, electronic configuration. Okay, so sodium, atomic number 11. Okay, that means we are looking at 11 electrons to place. So the first electron is going to go to the first energy level. First energy level has one shell, which is called 1s. It has got orbital, 1s orbital. A maximum of 2 electrons are occupied there, can be occupied in s orbital. Next you go, you still have 9 more electrons to place. So you're going to go to the next energy level. So 2s orbital, and 2s orbital can hold a maximum of 2 electrons. Now you're still left with some more electrons. So they are going to go to 2p. In 2p, a maximum of 6 electrons can be held. So you see, you have about 10 electrons placed like the noble gas, which is neon. Neon has 10 electrons. So the inner core is like that of neon. Okay. Now you have one more electron to place, and that goes in 3s. And that 1s. So if you look at it, last time we talked about that this belongs to the S block, and in the S block, it belongs to the first column in S block, first column in S block, and it is present in the third row or third period. So third row means it has got 3 energy levels. 3 energy levels. Okay, so that is sodium. Now this is called the ground state electronic configuration of sodium, which means like the electrons are just sitting there. But when these electrons get excited, or when the atom of sodium gets excited, then what happens? Then it in the excited state, means when it acquires energy, then what happens? It loses. Then sodium loses 1 electron. Why does it lose 1 electron? So that sodium can have electronic configuration like that of neon, which is 10, and that is a noble gas. And why noble gas? Because when it loses, then it has 8 electrons in last shell. Okay, now you're going to see this in the excited state, what it looks like. So here is the sodium. Now keep this in mind that this piece right here is the valence electron. Okay, this is the valence electron, and this valence electron is valence electron is equal to just 1, and this is the valence shell. This is the valence shell. That is the last shell number, and the highest shell number, as you can see, 3 is the highest. Okay, so the Lewis structure. So let's just, we need to draw these also. The Lewis structure of sodium looks like this. Just 1 valence electron you need to show in Lewis structure, 1 valence electron. Okay, now here's the sodium with its 1 valence electron, and so sodium with one valence electron. When it loses that one valence electron, minus one electron, then it acquires a positive charge, plus one charge. Okay, so then it looks like neon 10. Okay, so neon 10 has got then its electronic configuration of sodium ion. What does it look like? So sodium plus is 1s2, 2s2, and 2p6. And then the 3s is 0. So basically that's where it lost its electron. So you see now 8 electrons are here. So 8 electrons, these are the 8 electrons. So that's why it gets the octet. And it's looking like the electronic configuration of neon. That means, in other words, when sodium 11 loses that one electron, it acquires the positive charge, but 10 electrons now. So here there are 11 electrons, here there are 10 electrons. Okay, so that's one thing. So it got the noble gas configuration, right? It got the noble gas configuration and it acquired the octet. So you can look at it like this. Now, this is a very old middle school, diagram, which we don't usually use because it's just 3D. It's in 2D. So here's this first energy level and comes the second energy level. And then comes the third energy level. So in the first energy level, there are 2 electrons. These 2 electrons, these 2, right here. Then there are the 8 electrons, which is in the second energy level. 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons. And then 3s. So this is one piece right here, second energy level. And then 3s initially had 1 electron right here. And so this electron, when this electron leaves minus 1 electron, then what is left? You are left with 8 electrons in the last shell. Then the second energy level 2 becomes the last shell. So keep this in mind that this is energy level 1, energy level 1, energy level 2, and energy level 3. So then energy level 3 becomes vacant, means no electrons there. And the last shell is the energy level 2 in the case of sodium. Okay, then in that case, when that one electron leaves. So this is the valence electron, 1 electron. Okay, now that is the electronic configuration of sodium ion. Now let's look at where does that 1 electron go. That 1 electron goes to chlorine. So here is the chlorine. Chlorine. Seventeen electrons. So 1s2, 2s2, 2p6, 3s2, and 3p5. So if you count these, 2 plus 2, 4, plus 6, 10, plus 2, 12, plus 5, 17. So 17 electrons get accounted for. Now what happens? In this case, you see the inner core is neon, which is fine, but it has got 17 electrons, and so this is the valence shell. This is the valence shell. So let's look at the orbital diagram. Orbital diagram of chlorine. And then you can see how many electrons are unpaired. So this is the 3s2 and 3p5, 1, 2, 3, 3p5. So we see that the 2 electrons are here from 3s2 and 3p5 is always first singly occupied and then you pair them. So now you see here the 3p5 has 1 unpaired electron. So this is 1 unpaired electron. So 1 unpaired electron is looking to pair. Just it needs 1 more. electron so that it can pair. So this electron that sodium had given comes here. So this is now becomes +1 electron from sodium. Okay, so when this electron comes, it, the S becomes paired, and the P becomes paired. One of the electrons in the P orbital gets paired. So now chlorine will have, because it has taken that 1 electron. So here initially was chlorine 7 valence electrons. Okay, 7 valence electrons, 7 valence electrons. And when it acquires +1 more electron, what happens? It becomes chlorine 8. But it acquires, because it has acquired 1 more electron, it acquires a negative charge. Okay, so now we have, in this case, the electronic configuration is going to look like 1s2. So chlorine, with its initially had 17 electrons, right? And then when it takes 1 more electron, then it requires the chloride ion, which is fine, but there are 18 electrons. And now it begins to look like the argon. Argon has 18 electrons. So chlorine prefers to get 1 more electron so that it can look like argon. But sodium prefers to lose 1 electron so it can have electronic configuration similar to neon. So we show this in square brackets, okay, neon-like configuration. And similarly, chlorine prefers to gain 1 electron, so it can have the electronic configuration that of argon. Okay, so that's the reason why. So octet rule is the driving force, wanting to look like the nearest noble gas. That is the driving force. So now we see what does the electronic configuration of the chloride ion looks like. So it's here 1s2. So we are going to place 18 electrons. 1s2, 2s2, 2p6, 3s2, and 3p6. Okay, so it acquires that 1 electron, and then it's paired, it gets paired, and it becomes so when it gets paired, let me just put this in red. So this is going to just come here and pairs like in the opposite direction. Okay, so this is the last shell still, and there are 8 electrons here, right? So that's what makes it like completely filled up. So as you must have seen, this is the older model of chlorine. So here is this nucleus, and outside the nucleus is this energy level. This is the first energy level, this is the second energy level, and then comes the third energy level. So this is the older 2D models, not like, doesn't apply to all the atoms, but still it is there. So here we have the 1s2, and here is this 2s2 and 2p6. So this is again 8 electrons. So 1, 2, 3, 4, 5, 6, 7, and 8 electrons, right? And now the 3p initially had 7, 1, 2, 3, 4, 5, 6, and 7. And then that 1 electron when it comes, it will be present somewhere, right? It goes in the last shell. So that 1 electron comes here. 1 electron comes here, and that's how the chlorine gets the negative charge, right? And it has got 8 electrons total. That 1 electron comes, sits there, 8 electrons, a very happy state for chlorine. Okay, because now it's beginning to look like argon. Okay, and argon has a similar setup like that of chlorine, but this is actually chloride ion. Okay, now that's the 2 types. We've seen the very basic ones, but let's look at a few more ions. So this is one example. So in a way, this is like this part is overlapping with the chapter. What was that? Chapter 7, Ionic Bonds. Okay, so this is one example. Okay, now let's look at another example. of aluminum and oxygen. So aluminum is 13 electrons. So aluminum is 1s2, 2s2, 2p6, 3s2, and 3p1. So these guys, 3s2 and 3p1, are the valence electrons. So valence electrons are 3. So these are the 3 valence electrons. Okay, and now look at the inner core, 10 electrons, that of neon 10. So we see that aluminum, the 3 valence electrons are here. That's the Lewis structure. It's always good to see, how they look like. So that's the element. So it loses, it minus these 3 electrons so that it looks like aluminum. It looks like aluminum with +3 charge. Aluminum with +3 charge. 3 electrons lost, so it gives you +3 charge. Now, here's the thing with the aluminum's noble gas configuration. So we saw that, and when it loses, so if you look at it, 1s2, 2s2, and 2p6, then 3s2 and 3p1 are like this, 1, 2, 3. So 3s2 and 3p1, 3s2 is this, and 3p1 is here. Okay, now inner core is, like I said, of neon, and these are like the neon 10. So this is how aluminum looks like, okay, aluminum. But when aluminum loses those 3 electrons, then all it's left with is 1s2, 1s2, 2s2, and 2p6. Here, aluminum is 13. Here, aluminum is 10. Okay, and with that said, you also see then this 3s2 becomes 0 and 3p1 is 0. So we see this here, 2s2 and 2p6. 2s2 and 2p6 are, this is 8 electrons. Okay, so it has the noble gas configuration and it has 8 electrons. So this is 2 electrons here, 8 electrons here. When they combine neon, it looks like neon. So that is the ideal state for, sorry, this one would be, this should be 0. P0. Okay, now we see that that's the story with aluminum. But let's look at oxygen. What happens to oxygen? Oxygen has 8 electrons. Oxygen is 1s2, 2s2, and 2p, 2p8, no, 2p4. Okay, so in this case, the outer electrons, this is the outer electrons, the valence shell, 6 valence electrons. So how many oxygen needs? Oxygen prefers to accept 2 electrons so that it can look like neon 10, and have 8 electrons in the valence shell, in last shell. Okay, so oxygen 8 is going to accept 2 electrons, and when that happens, it becomes oxygen 10, but it will acquire 2 negative charges. Okay, so the oxide ions electronic configuration looks like 1s2, 2s2, 2p6. Okay, so these 2s2 and 2p6, 2p4, and here 1, 2, 3. So this is 2s, this is 2p, this is 2s, this is 2p. So here we have 2s2 and 2p6 is 1, 2, 3, 4, 5, 6. Here in this case, we have 2s2 here, and 2p4 is 1, 2, 3, 4. So you see there are 2 unpaired electrons. So when they get paired, then it's, it's an ideal state. So you're going to write this here, just so you get that. So these are why oxygen will make 2 bonds, or oxygen will have two negative charges, because it has 2 unpaired electrons. Okay, so what happens now? How are these ionic bonds formed? So this was all about, writing the electronic configuration of the ions. Now, what you're going to do is, let's make the ionic bonds. So, ionic bonds. So here is this sodium. As you guys know, sodium has, let's put it here, sodium has a plus charge and chlorine has a minus charge. Sodium has +1 charge, chlorine has a -1 charge. And so when they crisscross, the formula becomes sodium chloride, just NaCl. Okay, just a simple NaCl. Okay. In other words, here is this sodium with its 1 electron, and here is this chlorine with its 7 valence electrons. Okay, so what happens is that when this electron completely goes to chlorine, chlorine is more electronegative. It will pull that 1 electron automatically, so the electron gets transferred to chlorine completely. And that is what it leads those charges, so this is what's happening here. That is an ionic bond. Okay, let's look at the scenario with aluminum. So you have aluminum with plus these 3 electrons, and you have oxygen with 1, 2, 3, 4, 5, 6 electrons. Okay, so aluminum gives away 3 electrons. So this is all about balancing also. So here is this aluminum minus, so here, just keep it like that, -3 electrons, and aluminum acquires a +2 3 charge. Oxygen has 6 valence electrons, and it acquires 2 electrons that aluminum gives. And so oxygen gets 2 negative charges, but it has 8 electrons in its last shell. Okay, aluminum will also have 8 electrons in its last shell, but this is, what the scenario looks like. So here comes aluminum, which is with its +3 charge, and here comes oxygen with its -2 charge. Then what happens? Then this guy, this 3 comes here and 2 goes here. So what will you get? You're going to get Al2O3. Okay, aluminum oxide. So that's the formation of ionic bond and the charges. Let's see what else is left. Electronic configuration. Now look at the trends in the periodic table. Okay, yeah, trends in the periodic table. Back to the first chapter, trends. Okay, and this also means periodicity. Okay, so trends in periodic table. Okay, now here's a trend. There are many trends, but we are going to cover, one is the size, and when we talk about size, we are talking about the radius, atomic radius. Okay, one is the atomic radius. The second is the ionization energy. Okay, and the third is the electron affinity. Okay, electron affinity and ionization energy, they go side by side, both of them hand in hand. Okay, now Let's look at the first one, the size. The size, which one is bigger and so forth, whether the ions. So one is when we talk about the size, we are actually looking at the radius of the atom. So here is this nucleus. Okay, now nucleus, and from the side, from the side till here, this is called a radius. Okay, so thus the radius of an atom is depending upon, like the nucleus also, you know, the nucleus is smaller, the nucleus, and then, you know, what is the spread of the electron cloud, how does it, you know, work, those things. So remember that the size of the nucleus depends how many protons are there. So the heavier the nucleus is, it is going to exert a lot of influence. So here is this nucleus, huge big nucleus, and this nucleus has lots of protons, plus charges. Remember that there's plus charges, they're always going to have an attraction for the negative charges. So plus charges will exert an influence on the plus charges will exert an influence on the negative electrons. So we see that this is again, you know, small radius. So all this is the size of the atom, that is the atomic radius. In this case, I mean, size can be anything, but atomic radius, okay, is R. Okay, it depends on a few things. Number one, it depends on the nuclear size. You know, nuclear size means the total number of protons. It depends on that nuclear size of the nucleus, total number of protons, how many protons are there. And then as the number of protons increase, what increases? The nuclear pull increases. Nuclear pull increases. What else increase? As the number of protons increase, we also see that the nuclear pull increases. We also see the number of energy levels, or the number of shells, increase. And when the shells increase, what increases? Shielding effect increases. As you have more and more shells, obviously the inner shells are going to shield shield the outer shells from the nucleus. Okay, so these shells are playing a role. Okay, so Paulette has a question. How come the last part is determined to be the valence again? The thing you underlined. I don't know which one are you talking. I didn't see. The last part is always the valence. You know, somebody has to be the valence, right? So the one that is in the end is called a valence. That's just a location, the name given to the last electrons. So the thing that you should be thinking about is that which is the valence shell? The valence shell is always the highest shell number. Okay, Paulette, does that make sense?
Oh yeah, I was referring to the thing in red, but I get it now.
You get it? Okay, so the highest shell number is the valence shell. In this case, the highest shell number is the valence shell, this one. Okay, so it's not 3p5, it's 3s2 and 3p5. Okay, so these are the valence electrons and valence shell. Okay, so there are 7 valence electrons, you know, which we show like this. All right, now we have, so what was the next one? Akwi says that, say we were doing this for carbon, would it prefer to accept or give 4 valence electrons? Yes. If carbon was to make ionic bonds, then it can accept 4 electrons and it can give 4 electrons also. When it accepts 4 electrons, it becomes carbanion. And when it gives away 4 electrons, then it becomes carbocation. you know, so yeah, those are very important features in organic chemistry. So yes. Okay, so anyway, so now let's look at the size. Just give me 1 minute. So yeah, okay. Now, there is a trend in the periodic table, and a trend is that as you go in the same row, as you go from left to right, as you go from left to right, what happens to the size? The size decreases. The atomic size, the atomic radius decreases. So radius decreases. And when you go in the same in a same column, if you go from top to bottom, the size increases. So the radius increases. Okay, radius increases. So in this case, what we see is that, let us look at some of these elements now. Let's look at these elements that are in the periodic table. Give me 1 minute. Okay, yeah. So you have lithium versus chlorine, bromine, iodide. That's the top variation in ionic radii. Okay, so if you have lithium, which is the other one, lithium, beryllium, and then you have boron, carbon, nitrogen, oxygen, fluorine, and neon. So you see one thing is increasing here. Here, lithium has 3 protons. Beryllium has 4 protons. So number of protons. Remember, it's the protons that exert their power. Their nuclear pull is due to the protons. Okay, so the more the protons there are, the stronger the nuclear pull is going to be. So we have, as we see, that 3, 4, 5 protons, 6 protons, 7 protons, 8 protons, 9 protons, and 10 protons. Okay, and yes, the number of electrons are also the same. But as you go down from here to here, the size, the size is say from boron to neon, the size decreases very specifically. Size decreases very specifically, partly because these are the P block. These are in P block. So if you compare them, then boron has a bigger size than neon, because neon has more protons. So more protons in neon attract the electrons. Now keep this in mind, that this is in the same row. That means same energy levels. Same energy level means same shell. So the shell is still the same. That's not changing. Okay, so when it's happening in the same energy level, now all you're doing is increasing the size of protons, and the energy level is still the same. So as more protons, let me write this down here. As more protons are added to the same like as more protons are added. You can also say that more electrons are also added to the same energy level. Same energy level means same shell. Okay, so in the same shell, that means the distance from the nucleus is now the size of the nucleus is increasing. The size of nucleus increases. Okay, when the size of nucleus increase, what happens? The nuclear pull increases. Nuclear pull increases. So when the nuclear pull increases, what happens? The electrons are more, connected or are more attracted to the nucleus. Electrons are more attracted to the nucleus. So the electron cloud condenses. Okay, it becomes more squished. So that's how the size decreases. Here, these are in S block. So it's very important in which block they are. So this is S block. So even in the S block, yes, these two are going to be like, if you compare lithium and beryllium, lithium is bigger in size than beryllium. Okay, here boron is bigger in size than neon, or carbon is bigger in size than nitrogen, or oxygen is bigger in size than fluorine, and so forth. Okay, so that's one piece. Now look at it in the column. So let's look at it. This one was in the size, the atomic radii. So we are looking at in the, this might confuse you. Let me put this here. Top down in the same column. Okay, now here is, let's put this here on top, in the same period. So if you're comparing things in the same period, moving left to right is going to decrease the size. That's one piece. Next is in the same column. What happens in the same column? Same column, when you go from top down, the size increases. In the same period, the size is decreasing. For these reasons explained, all these points. This point, electrons are more attracted to the nucleus, and the electrons, they condense. In the same column, the size increase. Now, why does this happen? As you go from top down, okay, as you go from top down, what happens? That atoms in the same column, let's put this here, atoms in same column from top to bottom, okay. So in this case, what happens, that the size is increasing, size increases because number of shells increase. Number of shells are increasing here. In the top one, it was in the same shell. Did I put this here? Same energy level, right? So they are in the same energy level. But as here, the number of shells increase. More and more shells are added. More and more shells lead to the shielding effect. Shielding effect increases, means that the electrons, the electrons that are in the inner core or the inner energy levels, they are shielded by the electrons, like the electrons that are near the nucleus in that energy level. That energy level shields the electrons that are away from the nucleus. outer energy levels. Okay, so the shielding effect increases. So what decreases? The nuclear pull decreases. So then when the nuclear pull goes down, that means the electron cloud. Basically, electrons are present in the clouds. Okay, and those clouds are what? Clouds are energy levels. So the electron clouds, they expand. Okay, electron clouds expand, and therefore the size increases. All right, so that's for the neutral atoms from going from top down. Now let's look at compare the neutral atom versus the ions. Okay, which one is bigger and which one is not? So let's look at this one example. You have sodium and you have sodium ion. Which one do you think is bigger? Sodium or sodium ion? What do you think is bigger? Which one? Neutral is bigger. Why?
Because neutral energy of the electron composite that has almost
Yeah, so the neutral atom is bigger or the M. So here, remember that there are 11 protons. And here also there are 11 protons, right? Yeah, and here there are 11 electrons. And here there are 10 electrons. So what happens is that the size of the sodium is going to be bigger because here 11 protons are pulling 10 electrons only. And here 11 protons are pulling 11 electrons. Okay, so naturally, if there is one less proton, one less electron, so the electron cloud is more condensed, is more like squished, is more condensed. CONDENSED is more condensed. Okay, means more like squished. So because of that. Okay, let's look at another one. You have chlorine and you have chloride. Which one is bigger? Yeah, so the ion is going to be bigger. Why? Because here you have 17 protons just pulling in 17 electrons. But here you have 17 protons and there are 18 electrons, one more. Now, something else happens. When one more electron is added, fine, it's all that octet rule and all that is met and everything is fine. But remember that there is the negative and negative electron charges repel. Okay, there is repulsion. And due to that repulsion, the electron cloud expands. Okay, so it's basically the expansion and the contraction or condensed, you can say contract here also. Contracted. And here it's the electron cloud expands. Okay, it spreads out more. So in order to accommodate that one more electron spreads out. Okay, so that spread out creates that this is a bigger size. So that's one piece. Okay, now let's look at another piece right here. If you are given another example, okay, 1, 2, 3, and here you are given beryllium plus 2 charges, then you are given magnesium with plus 2 charges, then you are given calcium with plus 2 charges, and you are given strontium with plus 2 charges. Now tell me, all of them, that means have lost the electron. So which one is smaller and which one is bigger? which one is smaller and which one is bigger? Yeah. Beryllium is smallest and the largest. Strontium. So here, this is in these are in what? These are in the same beryllium. One second. So you have beryllium, then comes magnesium, calcium, strontium. So this is in the same column. Okay, same column. Beryllium will have the smallest, then magnesium, because strontium, remember that it's in the same column, more energy levels. So here, let's put this here. Strontium has more shells, less nuclear pull. And anytime the nuclear pull is less, what happens? The electron cloud expands. Shielding effect is also more. Shielding effect is increasing actually. Shielding effect increases. So that's how the nucleus is able to pull the electron clouds. Okay, now that's one piece. Now let's look at another one, which is the ionization energy. Okay, that's another trend. So size, we're looking at the trends, size. Now let's look at the ionization energy. Now, what is ionization energy? Ionization energy, ionization yeah. Ionization energy is okay, this is an older term, ionization. Ionization means to ionize. So in the past, right? In the past, that's the scientist, they only knew that metals can lose electrons. Okay, so they thought that is ionization. So losing of electrons was considered to be ionization. So that's an old terminology which got stuck. So losing electrons was and still is considered to be ionized. Now, the energy given to an atom to lose or get rid of that one electron or two electrons to give away its electrons is called ionization energy. Ionization okay, it's called ionization energy. That was the energy. So that was only applied to positively. So this energy only applied to positively charged species or cations, formation of cations. That's all, because they knew it. That's the only thing they knew. So it came first that time. Although technically, from English perspective, ionization should apply to making the negative charged species also. But historically, we only knew that you could only make positively charged species called the cations. So we only thought that this is applied to that. So we are going to just stick with it for now. Okay, now here is an very interesting thing about deionization. Very important. Now pay attention to this. Here is the trend. And the trend is that when you go from left to right in the same period, the ionization energy increases. Okay, means it would be difficult. It becomes more energy needs to be given to remove the one electron. So more energy needs to be given to remove electrons. Okay, as you go from left to right, as you move your finger from left to right. But when you go from top to bottom, so here is the top to bottom, and this is in the same column. Same column. What happened? The ionization energy decreases. Ionization energy decreases. Why does it decrease? Why does it decrease? This means that it's easier to pull electrons from the atoms because the size of atoms is increasing. And when the size increases, what happens? What decreases? The nuclear pull. Nuclear pull goes down. Nuclear pull goes down, right? Shielding effect increases. The electrons that are in the last shell, because now they are, like what is shielding effect? We already discussed that here is the teacher, okay? And here is the teacher. And this is the first group of students sitting in the first row. So the teacher can clearly see the first row of students. Then comes the next row. The next row is 1, 2, 3, 4, 5, 6. You see that the second row now, the teacher can't see very clearly because the first row begins to block, and comes the last row or the third row. And these guys are like so far away from the teacher. Now 2 rows are blocking these people who are sitting in the last row. And the fourth row is even more further away from the main, the epicenter in the class, the teacher. Okay, so this is how we see that in the first row, it's the teacher has more control. This row, there's more control versus this row, which is like now being, a little bit, the control is weakened, but the last one is the least control because these two are blocking the effect. So they can't see. So this is, so I'm going to just put this here. This is row 1, first row, second row, and third row. So the first row, so this is, these two will block the view. For the teacher as well as for the students also, further away. All right, now we see the next is the so that's the shielding effect. Okay, now let's look at this example here. All right, aluminum. Okay, now aluminum is heated at a very high temperature, and it becomes a gas. In other words, it melts, and then you keep heating it again, it becomes a gas. So in that gaseous state, that's a neutral gaseous atom. This is the neutral, Neutral, neutral gaseous atom of aluminum. Okay, now what's happening is that this is leaves that one electron is lost. This is one electron is lost. All right, so this is the, I have to get this here, minus one electron. It acquires plus one charge. Look at the ionization energy. Ionization energy, this is called the first ionization energy. Okay, and that is 580 kilojoules per mole. So when you remove one electron, you need to give this much of energy. So this is called first ionization energy. Okay, now you have aluminum with plus one charge, okay, still in the gaseous state. When it has got, remember, 3 electrons. So now you remove the second electron. And then it becomes aluminum plus 2. So this is called the second ionization energy. And the value of this one is 815 kilojoules per mole. Okay, so that's the second ionization energy. Okay, then comes aluminum with its plus 2 charge in the gaseous state. Now it loses the third electron and it becomes aluminum plus 3 charge. And that is after the third ionization energy. Now these have all been quantified, and that is 2740 kilojoules per mole. That's the third ionization energy. And you can continue to remove the electrons from outside. So if you have aluminum plus 3 charge and in a gaseous state, that's already the ion of aluminum, and you remove that one more electron, you can, then it will have aluminum plus 4, 1, 2, 3, and 4 charge. So then it will have the fourth ionization energy. And look at the value of that, 11,600 kilojoules per mole. That's the amount of heat that you need to provide, okay? And that is the fourth ionization energy, okay? So why is this happening? Why the fourth ionization energy is so like so high? Why? Why is I4 more than I3? Why? If you look at it, these are similar. And then I3 is more than I2. Why? I3 is more than I2. But I1 is similar to I2. If you look at it, more or less similar, just so this is still in that range. This is 580, almost like 600. This is 800, it's a little bit still in that range. But if you look at between the difference between the third and the fourth, that is a lot. That is 2,740. What's happening? Yeah, why? And the last one is even worse. Why? Look at this one, 11,600. That's a lot. The answer lies in the electronic configuration. Look in the electronic. Always, you should do this. Always check in electronic configuration, and then you can get the answers from there. So let's look at this. Ionization of aluminum. Aluminum 13. Okay, fine. 1s2, 2s2, 2p6, 3s2, and 3p1. So it is looking like this. 3s2 and 3p1 is this. Look at this here. 3s2 is this, and 3p1 is this. So that's aluminum 13. Now comes aluminum with plus 1 charge. So 1s2, 2s2. So instead of writing this whole thing, I'm going to just make it condensed so we can just focus on. So this is the neon. So I'm going to just keep it at that. So we focus on these guys first. So here is this neon 10, and we need to remove only one electron. So that is 3s2 and 3p. Now that one electron is gone, right? So this becomes 3p0, and this is the 3s2. You agree to that? So it first loses this one electron. It's easy to remove this one electron. So that's why the ionization energy is very low. Remember that it's the amount of energy that is given to remove, the energy given to an atom to give away its electron. And that is called the ionization energy. Excuse me. So we see here that the little bit energy is given and only one electron lost from 3p1. That's one thing. Next, let's look at Al2. What's happening there? Al plus 2. Okay, here is one again, neon 10. So 3p0 is there. 3p is 0, no electrons here. Then this becomes 3s1. So one electron only left. Okay, so here one electron is given from 3s1. So yeah, initially 3s1 was paired, but it's easy to remove one electron, from s orbital. It's easier because it's a small, orbital. Now comes aluminum plus 3. Why is this one last electron so difficult to remove? You see that? Why do you think that? So one is saying, say that again.
Because it's ruining essentially when the last part of the shell.
Yeah, so remember, we learned of this rule, the Hund's rule. Hund's rule. Hund's rule is that half-filled and or fulfilled. Oh God. Orbitals are more stable. Half-filled and fulfilled orbitals are more stable. This is the Hund's rule. Okay. Now, this one was half-filled, but here this was away from the nucleus. So this one is further away from the nucleus. So this guy, even though it was half-filled, it's actually not half-filled. The 3p1 is not even half-filled, but it's away from the nucleus. So it's easy to remove that one. After removing that, this person is, these two are paired, right? And fine, that is why we had to give a little bit more energy. That is why the same amount of energy was not given. 580 was not given. We needed to add a little bit more energy because comparatively, this is a stable orbital. This is a stable orbital. So in order to break that, that pairing, that bonding, we needed to give that one more energy to remove that. This also is by any means stable. So this is also a stable orbital. But at the same time now, it is also connected more to the nuclear. The nuclear pull is also there. So nuclear pull is stronger. Here, nuclear pull is strong. nuclear pull is strong. So it's not letting that one electron go. So first is that half-filled orbital, and second thing is that the nuclear pull is also stronger. So because of that, to break that stability, nuclear pull, that's pulling it, we need to give more energy is needed, more energy needed. So that's like about 2000 times, in that range. But when you have aluminum +3, which looks like 1s2, 2s2, 2p6, you see that this is a very, very stable situation. 2s2 and 2p6 is like this. This looks like this. 2s2 is this, and 2p6, every single electron is paired, and there are 8 electrons in the last shell. The last shell is the second shell, okay? And very difficult. You need, this is 8 electrons, fully filled. Each of the orbitals are fully filled. So you need to give large amount of energy to break that, that stability. So large amount of energy. I mean, in chemistry, see, that's the thing with the chemistry. You can create any kind of conditions. Okay, you can create any kind of increase the temperature, decrease the temperature, increase the pressure, add some cation, the catalyst and so forth. So you can do create any kind of conditions and get the results. But, how, it's a very extreme condition, 11,600, that's a lot of energy, okay? So large amount of energy needs to be given to remove the paired electrons. Pairing, anytime there is pairing, there is going to be, it's a challenge to remove that. I mean, you can, but so you see that. So this is one thing. Now there's also another. Let's look at this one. There are a few other examples. So neutral gases. Okay, another example. Some examples with exceptions. Now, which ones are those? There are some exceptions also. So what are those exceptions and what is that? So look at this. Beryllium 4 and boron 5. Okay, the first ionization energy of beryllium, that means first ionization energy means to remove one electron, is 899 kilojoules per mole. Okay, so this means beryllium 4 is 1s2, 2s2. Okay, simple. Next comes boron. Boron's first ionization energy is 800, lesser. This is an exception. Why? The answer again is in the electronic configuration. So look at boron 5 is 1s2, 2s2, and 2p1. So you see that this is a few things here. This is an S block, more close to the nucleus. Anytime S is very close to the nucleus. This is P block. So that's one difference. Because you're only removing one electron. So removing only one electron. Okay, from S block versus P block or P orbital, so all the elements that are in the S block will have a higher, S block has a higher ionization energy than the P block, which ionization energy is, comparatively lower. Comparison, it's always in comparison, not that, in comparison. Okay, so that's one thing. Next is you are only removing one electron that is unpaired electron. And it's easy to remove an one unpaired electron. So let's just put this here. Easy to remove one unpaired electron. So easy to remove one unpaired. Okay. This one is like, you know, again, this is fully filled. So very difficult to, you know, break that pairing. So that's one thing. So that's an exception, you know. So if you look at it, if there's a trend in the periodic table, this is just a, keep this in mind, that this is just a general trend. This is just a general trend, but not like, you know, but you have to look at the exceptions. Where are they placed, you know? So this is one thing. Next is, let's look at here, nitrogen, which has 7 valence electrons, no, 7 electrons. Its first ionization energy is 1,402 kilojoules per mole. Okay, that's for nitrogen. Now comes oxygen, 8. Oxygen, yeah, nitrogen is in group 5, oxygen is in group 6. So you should see that the ionization energy of oxygen should be more. Ionization energy of oxygen should be more, but no, the first ionization energy of oxygen is less, 1314 kilojoules per mole. Why? So again, the answer lies in the 1s2, 2s2, and 2p3. So here, look at this oxygen, nitrogen. This is the 2s2, and 2p3 is like this. 1, 2, 3. P's are here. So this is the 2s2 and 2p3 is here. So what do you see here? Half filled and full filled also, but half filled p orbitals are more stable. And when they're more stable, therefore, more energy, more heat is given to remove electrons from p orbitals. Okay, so that's the deal with nitrogen. That is why more energy is given. Okay, so the first ionization energy of nitrogen is more than the first ionization energy of oxygen. Oxygen has less. Now, why is that so? Look at this oxygen. So here's this oxygen. Oxygen is 1s2, 2s2, and 2p4. So here, there's already a problem. And what is that problem? So look at this here, 2s2 and 2p4. So 2s2, 1, 1, 2, 3. Okay, here is 2s2 and 2p4. 1, 2, 3, and 4. Okay, so you see, did I do this? Yeah, so 2p4. So here you see that first, we are talking about the first ionization energy. First ionization energy means removing that one electron. So this electron needs to be removed. This electron easily removed. Why? Why is this electron easily removed? Therefore, lesser first ionization energy. Why is that easily removed? How will that be easily removed? Yes, the answer is on the screen only. It's easier to remove that one electron. That is why the lesser ionization, first ionization energy of oxygen. Because you're removing an electron in a closer shell to the nucleus? No, because when you remove that one electron, what does that leave you with? The answer is on the screen. Yep. You will have these type of questions, guys. Yep. Come on. Arey Baba, what do you see on the screen? It's on the screen. It looks like people are sleeping or what? The answer is right here. If you remove that one electron, the one that I highlighted in yellow, this guy over here, and it's right here. When this electron is easily removed, therefore lesser ionization energy. But why is it easy to remove that one electron? Yeah. More energy which removes electrons as it moves across the right. The answer is on the screen. What is this? What is this? Say it loudly. Looks like people are tired. What is this on the screen? Yes, it'll be stable because it will become half filled, right? So right now it is like these two guys, trust me, you know, these electrons, they talk to each other. These guys are happy, paired, right? Happy, fine. Full-filled orbital, very stable. These guys are not happy when they see that one or person, you know, these two people are paired, you know, these two people who are lonely, they feel more lonely, you know, so they don't like that other person. So they want to get rid of him. So this is what happens is that when these three, so when that one electron is lost, when one electron is removed, then half-filled orbitals are left. Half-filled orbitals are left. So half-filled orbitals are more stable. Okay, when you remove that one electron, this guy, I already made it. So this one electron is locked. So then there are three, you know, half-filled, partially filled. Okay, so half-filled is more stable. Yeah, so keep that in mind. When one electron is removed from this is the 2p, this is the 2s and 2s2, and this is the 2p4. From 2p4, then half-filled orbitals, sorry. Half-filled orbitals are left, and so they are more stable. Okay. All right. Oh, now, you know, we can go on and on, but you can look at it. The same story is for, you know, other examples. So you have to look at main rule is, the basic rule is, just keep this Hund's rule in mind, that Hund's rule, that always half-filled and or full-filled orbitals are more stable. Okay, half-filled and full-filled orbitals are more stable. All right, so we get this. Now we have the next is the last piece is the electron affinity. Now electron affinity and the ionization energy is the same, but this one applies to the non-metals. So they realized that much later when they discovered the non-metals, that there are some elements that love electrons. Okay, love electrons. That is, they attract electrons towards themselves, attract electrons, and they form anions. And who are these guys? Vast majority of them are non-metals. All right, so so we have the we have now, okay, so this is the general trend again. In the same column, when you move from top to bottom, when you move from top to bottom, the electron affinity. So electron affinity, we say electron affinity as EA. The electron affinity decreases, goes down, decreases. So if you were to compare elements in the same column, the ones that are on the top will have more electron affinity than the ones that are at the bottom. Okay. Next is when you move from left to right in the periodic table. In other words, in the same period. What's happening? In the same period, the electron affinity increases. Okay, increases. So the elements, because remember that they're more close to the noble gases. So here's another thing. You're going to write on why. Why this happen here? Why? So why does it increase? It increases because sorry, because in same period you have the same energy level. And when you have the same energy level, what happens? Let me just put this here, LEVEL. In the same energy level, then you are there is an increase in number of protons. Okay, when there is increase in number of proton, there is also an increase in nuclear pull. Okay, so it's the nucleus that attracts the electrons. So keep this in mind, that nucleus pulls electrons. Okay, from outside also. Okay, so now here we have the nucleus pulling the electrons in the same. So besides this, that the non-metals are closer to the noble gases. So when they pull the electrons, or when one more electron is added, then they start looking like a noble gas. So non-metals are closer to noble gases. So accepting electrons helps them to get the electronic configuration like that of the noble gases. So accepting electrons helps the non-metals to get the electronic configuration like that of noble gases. Okay, so that's one thing. But why does the electron affinity decrease here? It decreases because in the same column, what is increasing? In the same column, energy levels are increasing. Energy levels increase. And anytime energy levels increase, what we are talking here about the energy levels, these are the energy levels. These represent the energy levels. And the teacher is the nucleus. So we see that as the energy levels increase, the shielding effect increases, right? Shielding effect increases. And when shielding effect increases, what happens? The nuclear pull is going to go down, right? So the nuclear pull goes down. And when the nuclear pull goes down, obviously the electron affinity electron affinity is what? Love for electrons. So electron affinity, love for electrons, goes down too. Less attraction on the electrons, less attraction for electrons, whether outside, inside, everywhere. Okay, so that's how you explain these. Okay, so I've written this for you guys, but you can kind of like, add up more stuff from your side on my notes. It's always a good idea. Okay, now let's look at some of the examples here. Okay, now a general term that they call is the energy is released. So energy is released upon the addition of electrons to a nucleus, to a neutral gaseous atom. Okay, neutral gaseous atom. Now, here, for example, here is a neutral gaseous atom. Okay, and it has accepted one electron, and fine, it acquires one negative charge and it's still in the gaseous state, plus a lot of energy is released. So all electron affinity is like an exothermic reaction. Okay, now look at these. Generally, if you were to look at the electron affinity of which ones are those? Electron affinity of like nitrogen versus oxygen versus fluorine. So you see that these are fluorine. Fluorine has more than oxygen and then nitrogen. No, wait, 1 second. Okay, yeah. Versus, so this is the neutral atoms. Neutral atoms. But look at this. Nitrogen with one negative charge. Very interesting here, guys. Versus carbon with one negative charge versus oxygen with one negative charge. What's happening here? When you have nitrogen with one negative charge, so that means, so keep this in mind, that here is carbon 6, here is nitrogen 7, and here you have oxygen 8. That's the protons, okay? But when we talk about, carbon with one negative charge, then it means 7 electrons. So here it is 1s2, 2s2, 2p, 2p2, and this becomes 2p3. Okay. Yeah. So why? So here is, look at this 1 second, 2p2, 2p2. So here, focus on this. 2s2. This is the last example we are doing. After that, we'll wrap up. So here is the 2s2 and 2p2. So 1, 2, and here's the 2p2. So this is vacant, right? So carbon can accept one more electron. Okay, so what does a carbon with one negative charge looks like? Then carbon with one negative charge looks like, this becomes carbon 7. So 1s2, that's the number of electrons. 6 electrons, here 7 electrons. So 1s2, 2s2, and 2p3. So how does this look like? This is 1, 2, 3. And what do you have here? Fully filled orbital, and this is half filled orbital, more stable. So half filled orbitals, orbital, more stable. So instead of carbon versus carbon minus 1, so carbon minus 1 is more stable than carbon plus 1. So more stable than carbon just by itself. after acquiring that one negative charge, after acquiring that charge. Okay, then let's look at nitrogen. Now nitrogen has 7 electrons. So this is nitrogen looking like 1s2, 2s2, and 2p3. So it's already stable. You see that this is the 2s2, and these are the 3. 2. So this is the 2s2 and 2p3. 2s2 and 2p2. So this is 2s2 and 2p3. So 1, 2, and 3. All right. So this is it's already half filled. So this is going to be good. But if you bring in nitrogen, 8 electrons, then it is very unstable. So 2s2 and 2p4. 2p4 is going to look like this. 1, 2, 3. So 2s2 and 2p4. And 2p4 is very unstable, like that. Very unstable. Okay? Because it is in here. Why? Because a repulsion occurs when one more electron is added. So, think about it. You have the whole room by yourself and you're very happy, but comes somebody else to share the room with you. I mean, obviously you won't like it. So same story here. This guy, when that one more electron comes, is not very happy. That is why the whole thing is very unstable. It never exists. You will never see this molecule. Okay? I mean, this atom. Same is the case with the oxygens, so same thing, you guys can figure this out, that, oxygen, when it acquires, with that two more, like it's oxygen, let's look at oxygen situation. So here this is oxygen, 8 electrons, 1s2, 2s2, 2p4. So 2s and 2p4, 2s2 and 2p4. 1, 2, 3. And here you have 1, 2, 1, 2. Okay, 1, 2, 3, and 4. So this is the deal with oxygen, but it prefers to, in this case, oxygen, oxygen can, oxygen would prefer to have these two guys, so that's why it prefers to have these two unstable, like this is unstable by itself, but these two electron need sparing. So that is why oxygen quickly absorbs, electrons from anywhere to get these two gates, because in that, when it does that, then it will have fully filled orbitals, which are going to be stable more. Okay, so it would prefer that one electron comes here, one more. Okay, all right, guys, so we covered that. Now the next thing is the chemical reactivity, and we will discuss, we are going to do the labs. So there is so much, we will discuss that piece in the lab, like which one is more reactive, which one is less reactive. Okay, so we could not, so we did do, the good part is from your chapter 7, I started off with the ionic bond. So I won't cover the ionic bond next time when we meet. We will just start off plain with the covalent bonding. Okay, so covalent bonding on Thursday. All right. Any questions anyone has? Okay, guys, so I'm going to now stop recording. And if you guys have any questions, just send me, and, thank you. Bye.